All right. Okay. Good afternoon. We'll start. Can you first confirm whether I'm clearly visible and audible? All right. Right. Clear, right? Okay. Listen. So as we planned, now we are starting fields lessons today, right? When it comes to our fields lessons, we have three main lessons, right? First, I'll give you a brief and the gravity of these lessons and what's the contribution of these lessons in our paper in the main exam, right? And then we'll get the start, right? So when it comes to fields lessons, this is what we have. Basically, we have three fields, right? First one is gravitational, right? This is what we are starting today, right? And then electric fields. Electric, this is also called electrostatic fields, electric fields, right? Then magnetic fields. These are the three fields lessons we have in our syllabus, right? These are the three fields lessons we have in our syllabus, right? So when it comes to the gravity, we are studying gravitational today. So when it comes to the gravity, it's like this. Right? From all three fields, we are getting 3 to 4 MCQs. We are getting 3 to 4 MCQs, right? It's definitely 3 because minimum there will be minimum of 1 MCQ from one field. There will be a minimum of 1 MCQ from one field, so it's around 3 to 4, right? Not always 3, right? Sometimes so 5 wage tibba times tibila thiyena. Even 5 has been there, right? But as an average, it's 3 to 4. And 3 is definitely 3 is there because from each field, 1 MCQ is coming. And there are no specific structured essays from fields, right? And we have an essay from fields. You have an essay from fields. Essay number 8, right? Essay number 8 is from fields. From fields. Then it can be any field from these three, or sometimes it can be a combination as well. This question is kind of similar in behavior to properties of matter. So, you know, in properties of matter also we had surface tension, viscosity and elasticity. And when it comes to the question comes either from one lesson there or as a combination, right? Same as that, right? For all fields you have one essay, right? For all fields we have question 8. Then here we can get like 4 marks, right? Say 3, I think 3 game move, definite 3, right? And here 30 marks for the essay, which means it is 7.5 out of 50. It is 7.5 out of 50, right? So basically it is 10.5. It is 10.5, right? So we call this a 10% lesson. We call this a 10% lesson, right? We call this a 10% lesson. We call this a 10% lesson, right? Now, in the reverse class also recently we have covered 2 10% lessons. Properties of matter was a 10% lesson, and matter and radiation was also a 10% lesson, right? And we are starting fields here today. That is also a 10% lesson. And in the reverse class this Saturday, I'll be starting current electricity. That is a 20% lesson, right? After current electricity, I'll be starting electronics in the reverse class. That is a 10% one. So likewise, that's all I know. That's it, right? Once current electricity and electronics are over, the syllabus is over, right? So we are starting electricity this Saturday, right? And we are starting gravitational here today. Okay then. So this is the gravity. Just have an idea what are the questions and question types you are going to get after learning this lesson, right? That is how it should be always. You have to focus on the marks now, right? We are just 18 weeks from the exam now, 18 weeks and 3 days now. We are on Thursday. We are on Thursday, right? That is exactly 18 weeks and 3 days. 18 weeks and 3 days, right? And focus on the marks. Focus on the marks. And this point is valid for any subject. If you are doing combined maths, then focus on the marks. What is the amount of marks you are going to get by the end of, say you did something like complex numbers. So after complex numbers, what's the mark you are going to get? So likewise, have a concern and an understanding about the amount of marks you are going to get from that particular thing, the contribution, right? So this is 10% like this. Okay. Now put the heading as gravitational fields. Put the heading as gravitational fields. Put the heading as gravitational fields. Participants here in the Zoom is kind of less today. Sometimes they might be on YouTube. I guess they are on YouTube. Right, anyways. Right, gravitational fields. Gravitational fields. Gravitational fields. Right. Listen. So first, let's see what a gravitational field is. Right. Well, let's see what a gravitational field is. Gravitational field means the field occurs around the mass. The field occurs around the mass is called a gravitational field. Right. The field occurs around the mass due to a mass actually. A field occurs around the mass due to a mass is called a gravitational field. Right. So we'll see how this field is going to occur. Right. You are learning this for the first time, right? So we are starting from scratch, from zero, right? We'll see how this field is actually exerted, how this is generated, and how these field lines are acting, and how the forces are generated, how the field intensity is determined. So likewise, there are more things to do, more new things to learn, right? Let's see. So first, write down below the field generated, 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 the field generated around the mass, the field generated around the mass, the field generated around the mass, the field generated around the mass due to a mass, due to a mass, around the mass due to a mass is called a gravitational field, is called a gravitational field. Around mass due to a mass is called a gravitational field, is called a gravitational field. Right. So you all know that 25 exam results are released now, right? So as a batch, 25 is a good batch as a batch. And what I wanted to say is you are also 18 weeks from the exam, just 18 weeks, right? When exam is in August, you will be getting your results in December, right? When exams are in August, you are getting your results in December, right? Now we are in April, right? So these things are going to be like decided very soon, right? So it flies even before we think. That's how it is. You have just 18 weeks for the exam now, right? And always the result reflects, right? The grade you have got reflects, the result reflects the amount of work you have done, amount of effort you have put, right? That's how it is, right? So if you are working, putting your fullest effort, you are working honestly with your own effort, fullest effort, right? You are never going to get something that you didn't expect, right? So if you didn't do anything at all, then you would get the relevant one, the relevant result, maybe F4, SO, whatever it is, right? Always that reflects the amount of work you have done, right? If you work hard for an A, right, at least you will stop getting B. So when your target is A, when you are targeting an A, don't target an A, right? So you have to target a rank, right? Target a rank, or else without just targeting 75, we have to target at least 85 from the paper, at least 85. That's how it should be. That's how it should be, right? So if you are targeting a district rank, right? If you are targeting a district rank, then you better work for an island rank. That's how it should be, right? Don't benchmark the exact point that you need to achieve, right? Have a benchmark of something beyond that. That's a better approach always. That's a better approach always, right? So work hard. We have just 18 weeks, right? So I will also hear out your results in December this year, right? Not yesterday, actually, day before yesterday, no? Results came out day before yesterday, right? The first call I got in night, it was around 11:30, 11:45, somewhere around, right? The very first call I got that day was the best result. That was District 38 here, District 38. Biocorp Malli right? 3 years and District 38. And his story is from the first attempt, he got, I'm just sharing this to show you his dedication, right? From the first attempt, he got BCC. He got BCC, right? And he came to my theory class that year, right? And he got BCC. He expected something like 3 Bs or something, right? 3 Bs wagega, but he got BCC. And then now on that same day itself also, he called me, and now since he knew that he didn't do some questions in especially in physics and chemistry, right? He had the intention of doing the exam again, taking the exam again. So after the exam, without waiting till the results, he started revision classes as well, right? But once he got the results, he called me and again asked for kind of a guidance, whether should he do something with that BCC or should I do again, right? So my advice was, now he has scored BCC. B means minimum he has scored 65 for bio, right? C means he has scored minimum 55 for physics and chemistry, right? Then taking it to 75 is not something as hard as that he was working for 55, right? Because the gap is just 20. That is not hard as that, right? Then he decided to take the exam again and worked hard, right? Personally, I know he worked around 16 hours a day, right? Personally, I know because he was kind of close with me, and sometimes he has shared his schedules as well, right? So personally, I know he worked for around 16 hours a day, and now he has got 3 years with a district rank 38, right? So that's a very good comeback. That's a very good comeback, right? See the dedication now. He had the capacity in the first try, even he had the capacity, but the thing was, for some reason, the full capacity didn't came out, right? But in the second one, he realized everything, and he knew his capacity and started again from zero and ended up entering a medical faculty, having a district rank 38, right? So that's how it is. That's how it is. Always first believe in yourself. You have the capacity, you have the potential. But first thing is you have to believe in yourself. You have the capacity, you have the potential, right? The only thing is you have to have a good focus and have a good plan, dedication, everything, and you have to work consistently, right? That's the only magic behind A levels. That's the only magic behind A levels, right? You can fact check what I say with your brothers, sisters, if there's anyone, or relatives, or anyone, right? That is how they are, right? Just talk to a person who has scored, who has got 3 years, something like that, or district ranks, island ranks. Talk to them and get an idea how they have worked, right? Everyone has the same story, right? Everyone has the same thing. There are points that they get failed several times in this journey. There are fluctuations, right? Success is always not linear. That is not a linear increase. That is not linear. It has ups and downs, fluctuations. And then at some point, you are going to start getting succeeded. So until you are reaching that point, we have to bear it up, right? We have to be patient. We have to believe in ourselves and we have to bear it up. Then once you reach that particular point, then hereafter, you will do everything without like any hassle. Right? ඒතකොට කියන්න දෙයක්වත් නැහැ. ගොඩක් වෙලාවට කියන්න දෙයක් නැහැ. ඔයාට මේතිලා ඔයා වැඩ කරන්න පටන් ගන්න පොයින්ට් එකක් එනවා. You will come to a point where you will start loving these subjects. අන්නේ පොයින්ට් එකට එනකම් පොඩ්ඩක් අමාරුයි. So you have to grab it. We have to be patient and grab this without giving up until we are reaching that point. So reaching that point is different from person to person, from student to student. That's how it is. That's the nature, right? Sometimes it can be a point somewhere in mechanics. Sometimes it can be a point somewhere in waves, optics, thermal, right? Electricity. So likewise, at some point we will reach there. But until then, don't get demotivated, right? Believe in yourself and behave accordingly, and wait until you are reaching that particular point. Definitely, that day is coming. That day is coming. If that has not come yet, right? For some of you, I know you are currently at like satisfactory levels, right? But if you feel like this is not true potential, true capacity, right? Then don't target that. Target something else, right? Now for the papers, now let's say you are scoring around 60, 65 these days, then target something like 85. Target something like 85. So once you reach there, say you have increased it to 75 somehow, then target 90, target 95. So likewise, always have a target which is beyond what you currently have. That's how it should be. That's how we progress ourselves, right? Okay, so that's what I wanted to share with these recent results we got, right? Always it reflects the effort you put onto this thing, right? So work hard. Just 18 weeks remaining. Just 18 weeks, right? Listen. 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 To graphically represent any field, listen, to graphically represent any field, we have something called field lines. To graphically represent a field, we have something called field lines. Right? So basically, by the field lines, we are representing the direction and magnitude of any field. In gravitational fields, we have gravitational field lines. In electric fields, we have electric field lines. In magnetic, we have magnetic field lines. So likewise, for any field, field lines are there. Now we are starting gravitational fields, you know. So let's see the features of gravitational field lines, and keep in mind that you are going to see the same in electric and magnetic as well, right? Same in the sense, same field lines, but in terms of features, they are different. But the purpose behind field lines, any field line, is same, right? That is to graphically represent direction and magnitude of a field, right? As an accident, write down features of gravitational field lines. Write down features of Heading features of gravitational field lines. Features of gravitational field lines. Features of gravitational field lines. Right. First one. We'll mention these features one by one. Right. First one. First one. Write down. Gravitational field lines are always perpendicular to surface. First one. Gravitational field lines are always perpendicular to surface. Gravitational field lines are always perpendicular to surface. Gravitational field lines are always perpendicular to surface. Right? Perpendicular to surface. Right? Like this. Perpendicular to surface. Second one. Gravitational field lines are always towards a surface. Gravitational field lines are always towards a surface. Gravitational field lines are always towards a surface slash mass. Towards a surface slash mass. Right? Towards, like this. Right? It is towards and perpendicular. Next one. Gravitational field lines are not intersected. 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 Right? So they cannot be intersected. Intersections, right? There cannot be intersections of gravitational field lines like this. Right? There cannot be intersections like this. Wrong. Right? 4. Closer the gravitational field lines, fourth one. Closer the gravitational field lines, higher the gravitational field lines, higher the gravitational field intensity. Closer the gravitational field lines, higher the gravitational field intensity. Closer the gravitational field lines, higher the gravitational field intensity. Alright, say we have this kind of a scenario. See, right, this kind of a scenario. Right, now towards this side, field lines are closer, no? Right, towards this side, field lines are wider. Then we represent gravitational field intensity using something called G dash, right? We'll see what's there. It's A and B. Then here, G dash B is greater than G dash A. Right? Closer the field lines, higher the field. Right? That is called gravitational field intensity. Don't worry about these words because you are going to see all definitions and the introductions, everything in the coming parts. Right? Mention this. Let's see a few examples. Of gravitational field lines. See, say you have a spherical shaped mass, a spherical mass. Then gravitational field lines are like this, perpendicular to surface, and it should be towards the surface. Perpendicular to surface and towards the surface. Perpendicular and towards surface, like this. Right? First one. You can take this down and I will give you some other masses. Then try them. Then you can try them after this. A cubical mass. Okay, try these ones. Try these ones. Oh, am I muted? Right. Thank you. Sorry. Sorry. Right. Check your answers. Check your. Right. Very simple. A simple idea. A simple idea. The purpose is graphically representing the direction and magnitude of a field. Right. Purpose is to graphically represent this. Purpose is to graphically represent this. Okay. Right. Let's move on. Finished, right? Let's move on. As the next heading, write down. Next heading. Explaining shape of earth as spherical. Explaining shape of earth. Explaining shape of earth as spherical. Explaining shape of earth as spherical using gravitational field lines. Explaining shape of earth as spherical using gravitational field lines. Right. See. So if it was a sphere, we know this is how field line should be. A sphere. If it was a sphere, this is how field lines are. If it was a sphere, this is how field lines are. Right. So we know. Listen. The story and the origin behind this is this one. We know there had been confusions from like a long ago about the shape of Earth. No, I think you have heard these stories in grade 6, 7, 8, those grades, right? So there were confusions about the shape of Earth, whether it's spherical, right? A set of scientists, they said it is spherical, and there was another set of scientists who said that is not spherical, that is like a plate. That is like a plate. Disk like a disk, like a plate. Right? සූර පප්පහෙන් බල්ලා දිනනවද දන්නවද මේ අර ඉන්ට්‍රෝ එකේ කියන්නේ රොටියක් වගේ තැටියක් වගේ මොකක්ද දෙයක් කියලා in සූර පප්පා cartoon, right? So that's how it was in ancient era, right? There were people who are saying it's spherical, and there were people who are arguing it as a disc shape, right? So those confusions were there, and general knowledge, who said the earth is spherical for the first time? Who was the scientist who found, or who said means who found the earth as spherical for the first time? Because initially people believe it as a disc, because now when we look around it's all flat. No, when we look around it's all flat, so they thought that it's this kind of an object. Who confidently said, I mean, who invented it, who found that the earth is spherical? Don't know. General knowledge. YouTube? Anyone? I think grade 7 or 8. Geometry or history. History or geometry. With geometry, what we call geography. History or geography. Grade 8, 7 or 8. It was Johannes Kepler. It was Johannes Kepler who found the earth as spherical for the first time. Right? Johannes Kepler. Right? His experiments were different. Now here what we are doing is, we are going to verify the same using gravitational field lines. Right? That it cannot be a disk shape and it should be spherical. We are going to prove it using gravitational field lines, and there are different other ways of doing the same proof as well, right? As a simple example, if you just look at the horizon at the beach, right? Horizon is also spherical, and if you look at the sky, sky is spherical. So likewise, those things are also there. Now here in gravitational fields, what we do is we are going to verify the same, prove the same using gravitational field lines. Using gravitational field lines, right? Now, if it was a disk kind of an object, this is how it should be, no? This is how it should be. If it was a disk type, if it was a disk type, right? Then gravitational field lines should be like this. In that case, gravitational field line should be like this. Right. Listen, we all know, that gravitational acceleration decreases when we are moving away from the Earth's surface. No, gravitational acceleration decreases, right? So in the space, at moon, on other planets, right? Gravitational acceleration is decreased, it's reduced, and kind of a floating anti-gravity effects are there, right? People are floating there, right? Moon ki adi you know that yesterday, not yesterday, today morning around 3 a.m. you know that a group of four people left Earth to land on moon, right? So this is the second time after 53 years, right? And 4 people from NASA, now they started their journey today morning to land on moon, right? So I think we will get an update soon. Moon is around 400,000 kilometers away. Moon is around 400,000 kilometers away. දැක්ක නැත්නම් ඒ videos බලන්න. launch එකේ videos එහෙම දැක්ක නැත්නම්. So it is around 400,000 kilometers away. It's a long journey, a super long journey. I think they are traveling around 200 kilometers per hour. The shuttle කියන්නේ rocket. The rocket is traveling around 200 kilometers per hour. Then you can do the numbers and see the time it takes, right? 200 kilometers per hour. The speed is this much. It was 200 when they were taking off, right? After the aerosphere, I think they can gain more speeds, right? So anyway, we will get an update soon. The launch was today morning. Was at today morning 4:03 for Sri Lanka. In Sri Lankan time, it was 4 a.m. 3 minutes past 4 a.m. Around 3 minutes past 4 a.m. Right. Okay. So what I was explaining was, so we know that gravitational acceleration decreases when we are moving above the Earth's surface, no? Right? Gravitational acceleration decreases. Gravitational acceleration is actually gravitational field intensity, right? Gravitational acceleration is a synonym for gravitational field intensity, right? Which means, see, now if you observe the behavior of these lines, right, when it comes to these electric field lines, right, they are scattering when we are moving away from the Earth's surface. When they scatter, right, we know the fourth feature of gravitational field lines. When they scatter, the gravitational field intensity decreases, right? Gravitational field intensity decreases. Gravitational field intensity means gravitational acceleration. G decreases, simply G decreases. But if the Earth was something like this, see, whatever the height you go above the Earth's surface, field lines are not getting closer or not getting wider, broader, which means gravitational field intensity in this kind of a surface should be uniform, but here it decreases because field lines are getting scattered, getting broader, right? So therefore, using these two we can say, also we can say, since gravitational acceleration above Earth's surface is decreasing, it should be a spherical shape. It should be a spherical shape. We can't say whether it's an ellipse or an exact sphere or what it is, but for sure we can say it is not a disk. It is not a disk type of an object. That is a spherical object. That is a spherical object. Right? That's how we argue here. Raise your hand if it's clear enough. Raise your hand if it's clear enough. Right? A simple one. Simple one. Right? Gravitational field. Right. Take it down again. These two diagrams. Take it down. Right. Okay. Let's explain this in point form. First point. Let's explain this in point form. First point. First point. Gravitational field intensity. Gravitational field intensity. Gravitational field intensity. Gravitational field intensity. Within brackets, gravitational acceleration. Within brackets, gravitational acceleration. They are same. They are synonyms. Huh? They are synonyms. Within brackets, gravitational acceleration. Gravitational acceleration. When moving up from Earth's surface, when moving up from Earth's surface, when moving up from Earth's surface, when moving up from Earth's surface. Right. Next point. Magnitude of gravitational field intensity. Magnitude of gravitational field intensity. Magnitude of gravitational field intensity remains unchanged. Magnitude of gravitational field intensity remains unchanged. Magnitude of gravitational field intensity remains unchanged. Remains unchanged. As field lines are parallel. 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 In a disc-shaped object. In a disc-shaped. In a disc-shaped. In a disc-shaped object. In a disc-shaped object. In a disc-shaped object. Right? Next one. Next bullet. Next point. But magnitude of gravitational field intensity, but magnitude of gravitational field intensity, magnitude of gravitational field intensity decreases as field lines are getting scattered. As field lines are getting scattered. As field lines are getting scattered. Getting scattered. When moving up. When moving up. When moving up. In a spherical shaped object. When moving up in a spherical shaped object. When moving up in a spherical shaped object. When moving up in a spherical shaped object. In a spherical shaped object. Next point. Therefore, shape of Earth. Therefore, shape of Earth must be spherical. 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 Must be spherical. Right. Questions. If gravitational field intensity decreases, does it mean gravitational acceleration increases? No, both are same, both decreases, both are same. Synonyms. Right? Next heading. Let's move on. Right? Ask if any questions. Right? Next heading, write down. Newton's universal gravitational law. Newton's universal gravitational law. Newton's universal gravitational law. Newton's universal gravitational law. Listen now. Stop all your work and listen. Stop all your work and listen. Right. So you know that famous story of apple, no? Right? When Sir Isaac Newton was under an apple tree, an apple falls, and he just thought something out of the box, and he questioned itself how and why it falls vertically downwards. So likewise, after doing some experiments, he found that it is due to gravity. But initially, this is what happened. Listen. So we know in the, up to this point in your learnings also, you have the same idea, I know. And for Newton also, he had the same. So initially he thought that this gravitational acceleration is always vertical. He thought that it's always vertical, right? And after first set of experiments, he found that it has vertical. But the thing was this. Listen, say this is our Earth. This is our Earth. This is our Earth. Let's assume you have an apple tree here in Arctic, and we have another apple tree in Antarctic, and we have another apple tree here, right? I know there are no trees in Arctic and Antarctic, but just assume. Now, listen. Now, if it falls vertically downwards, this apple here, which falls down from this tree, should fall down like this. What about this one? This apple here should fall down this way. If there is vertical downwards, this apple here should fall down this way. This one should fall down vertical downwards this way, right? Does it really happen? Right? Because this is the space. Ocean is around the earth, no? So this is the space, right? Right? What happens is it falls to the respective ground, no? It falls to the respective ground. Then initial finding as gravitational acceleration as vertical by Newton was contradicted simply because of this, right? Then again he did further researches, right? Further researches and experiments, and then he came up with this one, Newton's universal gravitational law, and this is 100% correct, and up until today everything is valid and applicable, right? And here he found about the magnitude and direction both, right? Now let's see how the direction comes, right? Now after this point onwards, you are going to change your thinking as gravitational acceleration is not always vertical downwards, right? That is not always vertical downwards. Up until this point, we also thought that it's vertical downwards always. No, that is not always vertical downwards. There are some other ways, a defined way of coming the direction, right? Direction එක නිකන් එන්නේ direction එක හොයාගන්න විදියක් තියෙනවා. Direction එක එන්නේ කොහොමද කියලා මෙයා මේක කියනවා. Right? එහෙම තමයි direction එක එන්නේ. Then I will link this again with what we know here, right? Okay. So මේක ආයෙ අදින්න එපා. Just keep this in mind. ඒක vertically downwards නෙමෙයි. That is not vertically downwards, right? Then in universal gravitational law, what he said was this. Listen. Gravitational force is not only between Earth and objects, right? It is between any two masses, any two objects, any two masses. So let's assume two masses as M1 and M2. Let's assume two masses as M1 and M2. Let's assume two masses as M1 and M2. Two masses, M1 and M2, right? M1 and M2. And this is the line which connects, see, this is the line which connects center of masses of these two. Line which connects center of masses. This is a line which connects center of masses of these two, right? So let's say distance between these two center of masses is R, right? And this is M1, right? What he said was, there is an attraction force. There is an attraction force between any two masses. There is an attraction force between any two masses along their attractions, no? Along the line which connects their centers of masses. Then they have attractions. They have attractions. Now, if we mark these attraction forces, this is how these forces are. They have attraction forces like this. Attractions. And he said this attraction force is defined as gravitational force, right? Listen again, this attraction force between any two masses was defined as gravitational force, right? That is a gravitational force. Otherwise, gravitational force is not something only due to Earth. That's everywhere when we have a mass, right? And he said that this force is proportional to the product of masses, and inversely proportional to squared distance between centers of masses. Right? මෙහෙම එකක් හොයාගන්න. And now using this law, we can explain everything. We can explain everything, right? So first we will take it down and then I'll explain these things again, aligning with this law. All right, take this down, take down the diagram. Okay, sorry. Write down the law in red. 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 attraction force between any two masses, attraction force between any two masses, attraction force between any two masses is gravitational force. Attraction force between any two masses is gravitational force. Attraction force between any two masses is gravitational force, and its magnitude and its magnitude and its magnitude and its magnitude is directly proportional to and its magnitude is directly proportional to and its magnitude is directly proportional to this one, directly proportional to product of masses, directly proportional to product of masses, directly proportional to product of masses, and inversely proportional to 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 distance between square distance between and inversely proportional to square distance inversely proportional to square distance between two centers of masses, inversely proportional to square distance between two centers of masses, inversely proportional to square distance between two centers of masses. Right? Listen now. Listen. Then he developed the equation like this. So from law we know, see, from gravitational law, we know F is proportional to m1 m2 over r squared. No, as the constant of proportionality, he introduced capital G m1 m2 over r squared, right? And this is the equation of Newton's universal gravitational law. Equation of Newton's universal gravitational law, right? The main equation we have here in gravitational fields. Main equation, right? So we'll introduce terms. You can prove it starting from here. Start from here and prove it. Then we'll introduce all terms. Right, introduce terms. F gravitational force, F gravitational force, F gravitational force, G universal gravitational constant, G universal gravitational constant, G universal gravitational constant, G universal gravitational constant. M1 M2 masses, M1 M2 masses, M1 M2 masses, right? R distance between centers of masses, R distance between centers of masses, right? So even though we write it as R, doesn't mean it's a radius. It's not a radius. Radius that's not a radius. Distance between centers of masses. Distance between centers of masses, right? Not a radius. Okay, listen now. Now this is what's happening actually. Listen. Stop all your work and listen. Listen. Right? Now, according to universal gravitational law, right? In between each and every objects, right? Each pair of objects, there are gravitational forces. Now, as an example, when I'm standing here, I have gravitational forces with these pens. I have gravitational forces with these cameras. I have gravitational forces with these laptops, mobile phones, lights, right? Everything with the board, everything, I have gravitational forces. So there are infinite number of gravitational forces, which acts on my body. There are infinite number of gravitational forces which acts on my body, right? But because of the massive mass of Earth, the gravitational force between myself and Earth is massive because it is proportional to M1 M2. No? It is proportional to M1 M2. Because of the massive mass of Earth, gravitational force between us or myself and the Earth is massive. That's why the resultant force acts vertically downwards, right? With respect to the surface that is vertical downwards. That's why resultant force acts downwards, and we are always attracted to Earth. That's why we are always attracted to Earth, right? That's why we are attracted to Earth. Otherwise, all the objects here, there are infinite number of gravitational forces, infinite number of gravitational forces acting on our body. So on your body also, there are infinite gravitational forces act, right? Even from your books, from your pen, from your anything, they exert gravitational forces. But because of the massive mass of Earth, right, gravitational force between myself and Earth is massive. So our resultant attraction is towards Earth. Our resultant attraction is towards the center of mass of Earth. That's why we are always attracted to Earth's surface, right? That's how we are always attracted to Earth's surface. Now, with that explanation, this issue is solved. No? Now, with this explanation, this issue is solved, right? Now, if a fruit falls from this kind of a tree, right? It falls towards the center of the Earth. It falls towards the center of the Earth, like this. Now, if it falls from somewhere here, it falls towards the center of the Earth, like this, right? So even if it falls from somewhere here, it falls towards the center of the Earth, right? That's how it occurs. Right? That is not vertically downwards. Right? If we consider a horizontal surface, then for that horizontal surface, that is vertical. But as an overall, that is not vertical. That is not vertical. This is how it works out. Now, even on this pen, there are infinite number of gravitational forces acting on infinite. Right? There are infinite forces. But when I release this pen, it is attracted towards the Earth's surface because the gravitational force with the Earth is the maximum one. Right? Otherwise, this pen and me also has gravitational forces. That's how it works. Right? Even with this chair, I have gravitational forces. With these lights, gravitational forces. Right? එහෙමයි තියෙන්නේ. Resultant is greater when the masses are greater. Higher the mass, higher the gravitational force. Right? Lower the distance, higher the gravitational force. So that was the exact explanation behind this. And this law is 100% valid up until today. And today also we are using, right? I mean, at present also we are using the same law without any issue, any hassle, because that is 100% valid. And they are universal laws, which means, listen, universal, what's the meaning? Universal means they are not limited to Earth, right? They are not limited to Earth. They are universal. They are universal. Then it is valid for whole universe. That is valid for whole universe, not limited to Earth, right? Earth is just another planet in the universe, right? These laws are valid for all the universe, up until our Milky Way, right? Up until our Milky Way, everything is valid. They are universal. As universal gas constant, right? This is universal gravitational law, right? We discussed universal gas constant in gases expansion. This is universal gravitational law. Universal, right? Even if we add mass, these things are valid. Even at moon, valid. At Jupiter, valid. Saturn, everywhere. Everywhere and anywhere in the universe, the law is valid, right? Okay then. Raise your hand if the idea is clear. Raise your hand if the idea is clear. This was the first idea you got about gravitational force. Okay, good. Right. Good. Now a small task. Find units and dimensions of G. Find units and dimensions of capital G. Newton's universal gravitational constant. Find units and dimensions of G. Units and dimensions of G. Find it. Send your answers. What are the answers? Okay, let's see. We are getting answers. Right. See, units. Units. If G is subjected, that is FR squared of M1, M2, no? Right? G is subjected FR squared, FR squared over M1, M2, right? M1, M2, right? Then substitute F is newtons, R squared, M squared, right? This is kg times kg. Then the unit is n kg minus 2 m squared, n kg minus 2 m squared, n kg minus 2 m squared, right? Yeah, your answers are correct. Then dimensions, dimensions of f times dimensions of r squared over dimensions of m1, m2. F is a force, mlt minus 2, mlt minus 2, r squared, l squared, m1, m2, m squared, right? Then L cube, m minus 1, t minus 2, L cube, m minus 1, t minus 2, L cube, m minus 1, t minus 2. Yeah, most of your answers are correct. Right? Take it down if anything. Units and dimensions. Right? Write down quickly. Right. As the next heading, write down. Next heading. Definition of definition of definition of gravitational field intensity. 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 Within brackets, gravitational acceleration. Within brackets, gravitational acceleration. Within brackets, gravitational acceleration. Right. Look at the board. We have another equation to define this with gravitational field intensity. That is called F equals mg dash. F equals mg dash. Right. F equals mg dash. F equals mg dash. Right. We call g dash equals g only at the Earth's surface. Right. We use g dash equals g only at the Earth's surface. Right. General term is g dash. Right. So the mg kilo that is mg dash. That is mg dash. Right. Gravitational force is given by mass into gravitational acceleration. Gravitational force is given by mass into gravitational acceleration. That is also called gravitational field intensity. Right. Take down the equation and highlight, introduce terms. Right. Take it down, highlight, and introduce terms. Take it down. Take it down. F gravitational force. Introduce F gravitational force. F gravitational force, right? Gravitational force. M mass, M mass, M mass. G dash, G dash gravitational field intensity. G dash gravitational field intensity. Gravitational field intensity. G dash gravitational field intensity. Slash gravitational acceleration. Slash gravitational acceleration. Slash gravitational acceleration. Gravitational field intensity slash gravitational acceleration. Right. Now, since we are to define gravitational field intensity, subject G dash. Subject is G dash from above. From above. G dash equals F of M. G dash equals F of M. Right? If dimensions are different, we know we are always define this as unit terms. Right? Unit terms. F is gravitational force, M is a mass. Right? Then gravitational field intensity is gravitational force per unit mass. Gravitational force per unit mass. Right? Gravitational force per unit mass in a gravitational field is called gravitational field intensity. Right? Now from this, we have been writing weights all the way from the beginning. The idea behind this was the same equation. Right? Weight is mg, no? Mg, g can be used only at the Earth's surface. Now, we didn't do any questions. We didn't do any questions so far considering universe, no? Considering planets, universe, we didn't do. Right? All the questions we had so far in Newton's laws, rotational motion, friction, circular motion, everything was close to Earth's surface. They were close to Earth's surface. That's why G dash was G. That's how you wrote weight as mg. But the holistic view, the big picture here is not just mg, that is mg dash, right? Mg dash, and when G dash changes, even if you put correct G dash, gravitational force comes, right? Okay, then subject is from above G dash is FOM. From above G dash is FOM. From above G dash is FOM. G dash is FOM. Fine. Write down the definition in red. Write down definition in red. Gravitational force. Gravitational force. Gravitational force per unit mass. Gravitational force per unit mass. Gravitational force per unit mass. Gravitational force per unit mass kept in a gravitational field. Gravitational force per unit mass kept in. Gravitational force per unit mass kept in a gravitational field. Kept in a gravitational field. Kept in a gravitational field is defined as gravitational field intensity is defined as gravitational field intensity is defined as gravitational field intensity is defined as gravitational field intensity. Right. Another small task. Find units and dimensions of G dash. Find units and dimensions of G dash. Find units and dimensions of G dash. Okay, finished. Let's see. Right. G dash. FOM. FOM. Right. Units of force over units of mass. Force is newtons, mass kilograms. Right. So that is nkg minus 1. Nkg minus 1. Right. Nkg minus 1. Correct. And we can do another thing like this. We know newtons can be expanded as, newtons can be expanded as, this is correct. Huh? This is correct. Then we know newtons can be expanded as kgm is minus 2. No? Units and dimensions. Kgm is minus 2 into kg minus 1. Kg to kg minus 1 cancels. Ms minus 2 remains. Because gravitational field intensity is gravitational acceleration. Gravitational field intensity is gravitational acceleration. Right? So that is what is proved here. In kg minus 1, that is ms minus 2. Right? You better mention both. Both are considered here as SI units. Both are considered as SI units. G dash, that is an acceleration. So you should get LT minus 2. Force is MLT minus 2 over mass M. Right? That is LT minus 2. LT minus 2. Right. Correct if any changes. Correct if any changes. Right. Let's move on. As the next heading, write down next heading. Determination of gravitational field intensity. Determination of gravitational field intensity. Determination of gravitational field intensity at a given point. Determination of gravitational field intensity at a given point. Determination of gravitational field intensity at a given point. Determination of gravitational field intensity at a given point. Right. So I will break this down to 3 scenarios. As first one, write down. First one, outside the surface. First one, outside the surface. Outside the surface. Within brackets, x greater than capital R. Write down. X greater than capital R. X greater than capital R. Outside the surface, x greater than capital R. Stop all your work and look at the board. Stop all your work and look at the board. Look at the board. Now let's say we have a mass here. Say mass is capital M. Right? And you are going to find gravitational field intensity at this point, which is outside the surface. At this point, which is outside the surface, say point X. Right? No, let's say point P. Say point P. This is O. Right? Listen. Now we are going to find gravitational field intensity at point P. Right? When such a question is given, this is how we do. This is how we approach. Right? First of all, we have to keep a mass. We have to keep a mass at the task point. Right? So we will be keeping a mass. Mass ka dila na hai. Right? We will be keeping a mass as simple m at that particular point. So keep a mass like this. keep a mass like this at this point, right? Keep a mass and mark the gravitational force between these two masses. Mark gravitational force between these two. Gravitational force is always along the line which connects centers of masses. Center of mass of this one is here. Center of mass of this mass is at its center. Then they have attraction forces like this. They have attraction forces like this. That is called gravitational force. That is called gravitational force, right? Then let's assume the distance from here to here as x. Let's assume the distance from here to here as x, right? Now what we do is we are applying our gravitational law. Right? Listen, this is the equation now. From Newton's universal gravitational law, we know F equals G m1 m2 over r squared. Right? Now apply it here. Then F equals G product of masses, capital M and simple m, over distance between centers of masses, x squared. Right? I need gravitational field intensity. Then expand F as mg dash. Expand F as mg dash. Right? We need at this point, no? At this point. Mass at this point is simple m. Mass at P is simple m. Mass at P is simple m. Then this is simple m g dash. Simple m g dash. Mass at this point into gravitational acceleration at the same point. Right? Equals g capital M simple m over x squared. Simple m2, simple m cancels. It should cancel off because simple m was put by us. It was not given. Because I asked you to keep a mass there for the simplification. Then it should ultimately cancel. It cancels. And g dash is coming here. G dash is gm over x squared. Gm over x squared. Right? This is g dash. So this is the gravitational field intensity at point P. This is the gravitational field intensity at point P. This is the gravitational field intensity at point P. Right? When you carefully observe this equation, see what you can see. When x increases, distance from here increases, distance increases, g decreases. Right? That's how, listen, that's how gravitational acceleration and gravitational field intensity decreases when we are moving away from the Earth's surface. Higher the distance, lower the g dash. Because g is a constant, mass of Earth is a constant. G is a constant, mass of Earth is a constant. Then higher the distance from here, higher the distance from Earth's surface, lower the gravitational acceleration, lower the gravitational field intensity. Right? That's how g decreases. Right? From the equation also we can verify. So basically this is how we do any proof or any determination of gravitational field intensities. Right? Raise your hand if it is clear. Right? Normal idea, very simple things. And as a lesson, gravitational fields is an easier one. Right? This is an easier one. And from all three fields also, easiest field is gravitational from all three. Gravitational came last time, 25 gravitational lava. Right? But ave godak kalagin. Right, let's see. Okay, take it down. Right. Right. This is the proof. X is the distance between center of masses, then X is measured from center, total distance from center, right? Because R here is distance between two centers of masses. So X is the distance from this center to this point. That's how it comes. Right. Now, uh, you know how to plot graphs, plot the variation with the distance, variation of G dash outside the surface in A, right? Variation of G dash with the distance. Plot this. Plot the graph. Innovations. What is our radius of mass? I haven't marked. R is radius of mass, capital R. Mark capital R here. Right? X is greater than R. R is radius of mass, like this. R radius of mass. Right? Okay, mark R is radius of mass. Right? What's the variation? G dash with X. G dash with distance. There is at X now. They are inverse. Right? They are inverse. An inverse curve. An inverse curve. An inverse curve. Right? From this you can clearly see, from this you can clearly see, higher the distance from Earth's surface, lower the gravitational field intensity. So it is theoretically zero at infinity. That is theoretically zero at infinity. That is theoretically zero at infinity. Right? Higher the distance, lower the gravitational acceleration, gravitational field intensity, and it becomes zero at infinity. It becomes zero at infinity. Right? Let's move on. Second one. Number two. Number two at the surface. Number two at the surface. At the surface, X equals R. At the surface, X equals R. At the surface, X equals R. X equals R. Right? For our clarity, now mass is on the surface itself. Mass is on the surface itself. Right? X is also up to X is R. X equals R. Right? So I will let you do this. Right? Follow the same steps. Follow the same steps. Follow the same steps as we did before and find G dash at this point. Right? At this point, at the surface. Right? At the surface. You can mark that point anywhere at the surface. Right? And find it. Same steps. Follow the same steps. Right, same thing. Keep the mass here. Simple M. Mark gravitational force as F. Attractions, that is always along the line which connects two centers of masses. Along the line which connects centers of masses. Right? Then apply gravitational law. F equals G m1 m2 over r square. Then F equals G m1 m2. Consider this as capital M, right? As before. Capital M, simple M over x squared over x squared. So we know F is mg dash. Then F is simple M g dash equals G capital M simple M. Now in this particular scenario, x equals r, no? In this particular scenario, x equals r. So r square. Then m to m cancels. G dash equals gm over r square. G dash equals gm over r square. G dash equals gm over r square. This is the gravitational field intensity at the surface. This is the gravitational field intensity at the surface. At the surface. Gravitational field intensity at the surface. On Earth surface, we say G dash equals G. On Earth only. On Earth only. Right? Okay, take it down. Take it down. Same type of a proof. Same type. Right. See? Now, if this was Earth, see, we know G dash equals G at Earth surface, right? G dash equals G at Earth surface. Since, write down in that, you can write down in that, since G dash equals G at Earth surface, write down, since G dash equals G at Earth surface, right? Then from this, we can say at the Earth surface, G dash equals G, no? G equals GMO r squared, right? Which means GM equals GR squared. GM equals GR squared at the Earth surface. GM equals GR squared at the Earth surface, right? For any other surface, right? Instead of G, we are using G dash. Instead of G, we are using G dash, right? Take this down. Usually we use this to convert capital G to omit capital D, omit capital G, right? Usually, આપણે capital G का simplification लेके omit करा करना मैं expressions use करना these expansions, right? Take it down. Gm equals GR squared. Next one. Number three, inside the surface. Number three, inside the surface. Number three, inside the surface. Number three, inside the surface within brackets x less than r. X less than r. Inside the surface. X less than r. X less than r. Right. Then radius of mass is this one. Radius of mass is r, right? And you are going to find gravitational field intensity at a point which is inside the surface, like this, right? To that point, distance is x. Say point P. Point P. Point P. Take it down. Right now, there's a small difference. Listen first. Listen. My explain karna. Listen. Listen. There's a small difference. Difference is center of mass of this sphere is this mass. Capital M is here. Center of mass of capital M is here. Center of mass of this object is here. Then attraction force, gravitational attraction force exerts like this. Gravitational force exerts like this. Gravitational force exerts like this, right? Gravitational force exerts like this. The thing is this. Only the mass inside this boundary, is contributing the center of mass here, right? Then mass of the boundary inside should be found now, right? Always, right? Oh, these other cases also it's valid. Always mass inside the boundary is valid. In the first case also it was there. In here also that's there, right? Now here also, now the boundary is inside, right? We are inside the surface, and mass inside the surface should be substituted, but that we don't know, which means we have to find it out. Let's assume mass of this part as m dash. Let's assume mass of this part as m dash, right? We all know m equals 0, no? We all know mass equals, we all know mass equals 0. Apply this for these two scenarios. Total mass, capital M. Total volume, 4/3, 5 capital R cube. Rho. Let's assume density of this substance as rho. Alright, assume karna. It will cancel off. Then for this small sphere, apply this again. M dash equals 4/3, 5. For small sphere, no? Radius is x cube. Rho. Divide these two. Then we will get m dash. These two cancels, 5 to 5, rho to rho cancels, right? Sorry, x cube. Then subject m dash. M dash is mx cube over r cube. So likewise, the difference here is, you better put some asterisk mark here. Make a poddak venas. The difference here is mass of the part inside our boundary should be determined separately, right? Mass of the part inside our boundary should be determined separately, right? Because the total mass is not contributing. But always mass inside the boundary contributes. Right? Okay. Then first find this out. Take this down and find this mass m dash. Any questions? For first instance, can we take g dash equals g if the earth surface? That is not at the earth surface, no? That is above. No, that is above. Take earth surface එක වෙන්න බෑනේ. ඒක surface එක නෙමෙයි, that is above. Second එක විතරනේ surface එකේ තියෙන්නේ. Right? Right? Earth surface means only at the surface. Not above the surface. At the surface. Right? Take it down. And now you can find this out. Right? Additional part එක කරලා ඉවරයි දැන්. Additional part එක තමයි මේක. Now m dash is known. Now you can write the gravitational force and find g dash. Find g dash. Now you can write the gravitational force and find g dash. Right? What are the answers? Put some asterisk marks here because this is a little bit special case. Anyone? M dash is found now. M dash is known. Gravitational force is between that mass M dash and simple m that we kept here. M dash and simple m that we kept here. Gravitational attraction is between M dash and M. Gravitational attraction is between M dash and M. Between M dash and M. Gravitational attraction is between M dash and M. Any answers? I will start in 2 minutes. Any answers? GMXO R cube. Good. Correct. Good. GMXO R cube. Good. See? Now, gravitational force is F equals G M1 M2 over R squared. Right? F is, now in this case, one mass is M dash. The other one is simple M over distance is X squared. Right? So we know F can be expanded as mg dash. F is mg dash, simple mg dash, right? Equals gm over x squared, keep it aside, and we have to plug m dash is here, capital mx cube over r cube. Then simple m to simple m cancels. X squared to x squared cancels, only x remains. Then g dash is gmx over r cube. Gmx over r cube. Gmx over r cube. Gmx over r cube. Right. Now, since it is done, right? If it is done, plot the variation of g dash. Now we are inside the surface now. G dash with distance. Plot this variation. G dash with distance. Right? We have got the equation now. Plot g dash with distance. What is the shape? What's the shape of the graph? You can say whether it's inverse, mx plus c, mx minus c, minus mx squared, m root x. What is the shape? Right. Anyone? What is the shape of the graph now? Right. Give me 1 second. Right. See, we are plotting g dash against distance. Then distance term here is x. Right. Graph plotting g dash equals gm over r cube x. Right. Gm over r cube x. Right. Now x is acting as d here, distance. Distance means x. Then x. And whatever the term it is as a product with independent variable is gradient, and g dash is y. G dash is y. Right? That is y equals mx. Y equals mx. R is a constant, radius is a constant. Then all gm over r cube is a constant. Gm over r cube is a constant. Right? Then variables are only g dash and x, y equals mx. Write down. Y equals mx. What's the idea now? Gravitational field intensity increases linearly inside the mass. Right? Gravitational field increases linearly inside the mass. Right? And that is 0. That is 0 at center. That is 0 at center. It is 0 at center and it increases linearly inside the mass. Right? Take down. So it behaves differently when we are inside the surface and outside the surface. Inside the surface it increases, but outside the surface it decreases. Up until infinity it decreases. Inside the surface it increases. Right. Now another small task. So before that, any questions up to this point? Any questions up to this point? Third instance. Can you explain third instance again? Is it clear now, or did you ask the question before? What about now? Raise your hand if it is clear enough and ask if any questions. Raise your hand if it is clear enough up to here. Right? Or if you got any questions, forward your questions. Now clear, right? Okay. This is a little bit special scenario. Always gravitational field or the gravitational field intensity is always due to the boundary which is inside the surface, right? This is special, and you will see a comparative case when we are moving to electric fields also, right? There are very comparative cases, right? So this is one of those, right? Okay, then if no any other questions, let's move on. Right, as an next heading, take down, write down next heading, variation between gravitational field intensity, variation between gravitational field intensity variation between gravitational field intensity, variation between gravitational field intensity and distance, variation between gravitational field intensity and distance for a given mass, for a given mass, for a given mass, for a given mass. Right. One question, listen. I didn't mention this, right? Think logically and tell me. Is gravitational field intensity a vector or a scalar? What about it? Gravitational field intensity. Is it a vector or a scalar? Gravitational field intensity. Is it a vector or a scalar? G dash. G dash. Is it a vector or a scalar? Vector or a scalar? Quickly. Vector. Vector. Yeah, it's a vector. It's a vector. Because its direction is towards surface. It has a direction. It has a direction. It's a vector. It's a vector. Or simply, gravitational field intensity is gravitational acceleration. No? Gravitational acceleration is a vector. Right? Its direction is towards surface. අපි features වල කිව්වනේ. under features of gravitational field lines. හරි ඒකම තමයි. features වල කිව්වා. ඒක direction එකක් තියෙනවා. direction එකක් තියෙනවා නම් එයා vector එකක්. හරි. Then this is what we are going to do. Say this is a mass. This is a mass. Right? Now we are going to plot the variation. We are going to plot the variation of gravitational field intensity with distance. Right? Gravitational field intensity G dash with distance. Right? You can separate these boundaries like this, and separate parts are already drawn in the previous proofs. Right? So you can connect them accordingly and complete this. Right? Try this. I need the variation of G dash. I need the variation of G dash with distance. Right? Need it for both sides. Right? For both sides. I need it for both sides. Right? Quickly. 2 minutes. Right? Finished? Right. So we know direction of G is towards the surface. No, direction of G is G dash is towards the surface. 1 second. Right. Direction of G dash is towards the surface. Then this side, at this side, it should be towards the surface like this. At this side, it should be towards the surface like this. Right. So I'm going to assume leftward ones as plus. Then we know from center to surface, it increases linearly. We proved the last proof we did. It increases linearly, and it was gm over r squared at the surface. It was gm over r squared at the surface, and it decreases beyond the surface like this. It decreases beyond the surface. It decreases beyond the surface. Since there is a vector, direction of G dash just after this point is opposite. Then it should be in the opposite direction like this. This value is right, same value but opposite direction minus gm over r square. Right, this is the variation with distance of G dash for a given mass. Take it down. Now I have collated the previous graphs together. Right? We show these shapes, we show these variations in the previous parts. Now I have collated them together. Take it down. Okay, finished. Keep this in mind, right? Even for MCQs, you are getting related questions, right? But questions to think based on this. Keep this shape, the rough shape in mind. And you will see more of these curves in electric fields also. Right? Now this is the radius. Put radius as capital R. Capital R. Right. Okay. A considerable part here is over. Raise your hand if everything is clear up to this point in gravitational fields. Raise your hand if everything is clear up to this point in gravitational fields. 3, 4, 5, 4, 5. What about the ones on YouTube? Can you put your comments? Right. So okay, here. All good? Ask if any questions. I can give you like 1 minute for questions if there's anything. No questions. Right. So it seems no questions. Right. Okay. Then hereafter, you will see some questions, sums of the related area that we discussed. Right. So before doing the sums, first we'll have a break now. Right. We'll have the break, and I will start the sums after the break, and the other parts after the sums of here. Again, we will be touching something on potential of a point and energy components in a gravitational field. Right? Those are the things coming up. Those are things coming up in the rest. Right? Okay. Then let's have a break of 20 minutes. Let's have a break of 20 minutes. Right? So we'll regroup by 6:20. We'll regroup by 6:20, and I will start off with the sums of the areas. Our examples will move on. Our examples from these areas you learned. Further, and my main focus today is covering the theory parts. Then we'll be moving on. We'll be moving on to the rest of the theories, right? But to get the idea, we'll see like 2-3 examples, and we will practice all types of questions next day with the tube, right? We'll practice all types of questions, all types of questions here in gravitational fields next day, right? Okay, then let's regroup by 6:20. Okay. Right. Right. Okay, I'm audible again, right? Okay. Right. First example. See, first example, example one. First example. See, let's see some examples. Example one. Example one. Write down, write down, write down. Determine, write down. Determine, determine, determine gravitational field intensity. Determine gravitational field intensity. Determine gravitational field intensity. Determine gravitational field intensity at a point located. Determine gravitational field intensity at a point located. Determine gravitational field intensity at a point located. Gravitational field intensity at a point located 2r distance away. 2r distance away. At a point located 2r distance away. At a point located 2r distance away from center of 2r distance away from center of 2r distance away from center of a planet of center of a planet of mass m and radius capital R. 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 Okay, take this down and give it a try. Now you know how we did before, right? Take it down and give it a try. Start now. Take it down and give it a try. Start now. I need gravitational field intensity at this point, 2r distance away. 2r away. A distance 2r away. Right? 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 Any answers? You can try before I do, right? Use the idea you got from the previous three proofs. Use the idea you gathered, you gain, the knowledge you gain from the three previous proofs, right? And try it. Any answers? GMO 4R squared. GMO 4R squared. Yeah, correct. Good. See, keep the mass here. Same thing. Keep a mass here. And mark gravitational force. Mark gravitational force between these two, F and F. Right? Then apply gravitational equation G, M1, M2. Right? Let's assume this as simple M. Then capital M, simple M over distance between two centers of gravity is center of gravity, two center of masses 2r, then 2r whole thing squared, 2r whole thing squared, right? So we know F can be expanded as mg dash, right? Then F is mg dash equals G capital M simple M over 4r squared, simple M to simple M cancels, we need G dash, that is Gm over 4r squared, Gm over 4r squared, Gm over 4r squared, Gm over 4r squared, right? Simple as that. Simple. Simple as that. Take it down. Take it down. Let's try another one. Example 2. Let's try another one. Example 2. Example 2. Write down. Write down. Write down. Weight of weight of weight of weight of an object at Earth's surface. 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 Weight of an object at Earth's surface is 400 newtons. Weight of an object at Earth's surface is 400 newtons. Weight of an object at Earth's surface is 400 newtons. What would be the weight of same object? What would be the weight of same object? What would be what would be what would be what would be the weight of same object? What would be the weight of same object? What would be the weight of same object? If it is taken, if it is taken, if it is taken, if it is taken, an additional height, an additional height, if it is taken, an additional height equivalent to radius, additional height equivalent to radius of Earth. If it is taken, additional height equivalent to radius of Earth from the surface of Earth. Additional height equivalent to radius of Earth from the surface of Earth. Additional height equivalent to radius of Earth from the surface of Earth. From the surface of Earth. Right. Right. So initially this mass is at the Earth surface. Right. That is at the Earth surface. That weight is given. And then it is taken. It is taken. Now let's say radius of Earth is r, not given, let's assume, right? Now in the second case, it is taken an additional distance equivalent to radius of Earth, right? So somewhere here, something like this. These two are the two scenarios. These two are the two scenarios. These two are the two scenarios. Right, right, right. Okay, any answers? Right. Listen, I will give a small hint. Now, we have been writing weight as mg. Mg is valid on the Earth's surface. Mg is valid on the Earth's surface, right? Now, as a common equation, weight should be mg dash, no? Because when g dash changes, weight changes. When g dash changes, weight changes. So, weight is mg dash. Or simply, weight is the gravitational force, isn't it? Weight is mg dash. Weight is the gravitational force. Right? F equals mg dash. Weight is the gravitational force. So simply, what we write as weight of an object is the gravitational force. M into G. Right? Gravitational force. G is valid only at the Earth's surface. Right? For any point as a general equation, it is given by mg dash. As a general equation at any point. Right? A general equation at any point. Weight equals mg dash. Any answers now? $100 Newtons. What else? Others? 100 Newtons. Good. Others? Any different answers? Any different answers? Okay, I will start in 2 minutes. Try by your own, right? Somehow try by your own. If you can get the answer before I discuss here, right? Means you have understood this perfectly. Right? I just give you an hint. Give you a hint. Right? Weight is gravitational force. Weight is mg dash. That is gravitational force. Weight is the gravitational force. Okay, let's see. See, simply idea is this. We know F equals G m1 m2 over r squared, right? F equals G m1 m2 over r squared. Gravitational force is the weight here. Gravitational force is the weight. Gravitational force is the weight. So let's assume mass of Earth as capital M and mass of this object as simple m. We'll assume it will cancel off. Mass of Earth as capital M, mass of the object as simple m. Right? Now, what if you apply the same equation for these two scenarios? What if you apply the same equation for these two scenarios? Because F is gravitational force, that is weight. F is gravitational force. Gravitational force. Right? Gravitational force can what the weight. Gravitational force means weight because there is mg dash. F equals mg dash. That is weight actually. That is what it creates weight of the object. Weight. Gravitational force can weight. Apply this for these two scenarios. First scenario, F is given as 400, no? 400. F is given as 400. Then 400 equals G capital M, simple M. Now we add here, right, R squared. For the second case, say F equals G, capital M, simple M. We add here now, then total distance between centers of masses 2R, then this is 2R whole thing squared. Divide these two. F over 400 equals, this is GMM over 4R squared times, this is, division is the multiplication with reciprocal, this one. GMM to GMM cancels, R squared to R squared cancels. F equals 400 over 4, 100 newtons. Then weight of the object becomes 100 newtons when it is at this point. Weight of the object becomes 100 newtons when it is at that point. Weight becomes 100 when it is at that point. Weight becomes 100 when it is at that point. Mass is constant, only the weight changes because G dash changes. Right? Listen. Now, weight is known. Weight at this point is known. Now, can you find gravitational field intensity at this point using the weight now? Give it a try. Find gravitational field intensity at this point using this weight you got. Right? Now, without following these steps we follow before, now easily we can do it through this. Right? Since you know the weight here, weight is known means gravitational force is known at this point. Then find gravitational field intensity at this particular point. Say this is GB. Gravitational field intensity at this point. Find GB. Something additional. 100 is correct. Take it down if you didn't do. And find GB. That's it. I need GB. GB means gravitational field intensity at point B. I need gravitational field intensity at point B. My hint is mass remains constant. Mass එක කියන එක කොහොමද වෙනස් කරන්න බෑ. Mass remains constant. Right? Mass එක change කරන්න බෑනේ. අරන් ගියා කියලා. Mass is constant. Only gravitational field intensity changes. That's it. GM of R is not given. Right? So I need it numerically with a number. Numerical value. We can find the numerical value now. Two 2.5. Yeah, it's 2.5. It's 2.5. Right? Now, if you apply this at Earth's surface, see, at point A, at Earth's surface, at the Earth's surface. So we know weight is mg dash, but at the Earth's surface, g dash equals g at the Earth's surface. G dash equals g at the Earth's surface. Right? Then weight is given. Weight should be 400 equals m. G dash is g, no? G is 10. Mass is known. This mass is 40 kilograms. This mass is 40 kilograms. Now, apply the same at point B. Apply the same at B. At B. At B. Weight equals mg dash. Right? Weight at point B is known 100. Weight at point B is known 100. 100 equals mass is 40. Right? G dash. Then simplify. G dash equals 2.5. G dash equals 2.5. Right? That is what it makes the difference in weight. Mass is same. Mass is same. But weight is different. Weight is changed because G changes. G dash changes. Right? When we are moving away from the surface, G dash changes. When G dash changes, weight changes. Right? Take it down. So these are the connections in between. These are the connections in between. Right? We'll try one last question from this type and going to move on to the energy aspects. Question name example. Example right. Write down below with a red pen. Write down below with a red pen somewhere here. Mass remains unchanged. 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 Right. Example 3. Example 3. Example 3. 3. Write down. Find the ratio between. Find the ratio between. Example 3. Find the ratio between. Find the ratio between. Find the ratio between gravitational field intensities at surface. At surfaces. Find the ratio between gravitational field intensities at surfaces. At surfaces of two planets A and B. 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 Two planets A and B. Having given attributes. Having given attributes. Having given attributes. Two planets A and B having given attributes. Having given attributes. Okay. Right. These two are the two planets given, A and B. This planet is a planet of density 2 rho, radius r. This is a planet of density rho, radius 2r. Right? I need the ratio between gravitational field intensities at their surfaces. Ratios between gravitational field intensities at their surfaces. Right? Right? අපි surface එකට equation එකක් ඕනනම් prove කරලා තියෙන්නේ. ඒක ඕනනම් use කරන්න පුළුවන්. We proved the equation at surface. G dash equals gm over r squared. That is proved. Right? So you can use it at once if needed. Right? Right now? Right? Anyone? Oh. Anyone? My hint is when density and radius changes, mass changes. Right? When density and radius changes, mass changes. So you have to factor it. You have to take that into account. Right? That's the point. It changes here. That's what it changes here. Right? Right. 1 to 2. One has got 1 to 2. Let's see. It's a possible one. 1 to 2, it's possible. Possible. I will start in like 2 minutes again. Right, right. Some of 1 to 2 is deleted. So you are revising. So if you got a revised answer, send it again. Let's see. Time is enough. Let's see. So we know gravitational field intensity at surface can be written as GMO r squared. No? Is GMO r squared. GMO r squared. Right? This is a proved equation. A proved equation. Now mass changes. Since mass changes, let's modify this equation before applying. Right? Let's modify this. We know mass can be written as V rho. No? M equals V rho. Then V rho over r squared. Right? Over r squared. Then we know G rho over r squared, volume of a sphere is 4 over 3 phi r cube. Volume of a sphere is 4 over 3 phi r cube. Arne? M එක කියන්නේ V rho, M is V rho, V කියලා කියන්නේ volume of a sphere, that is 4 over 3 phi r cube. Then this r squared to r cube cancels. Right? So it says G dash equals, it says G dash equals capital G. Right? 4 3 ekku තියෙනවා. See, 4 3 capital G 5 4 3 capital G 5 rho r 4 3 G 5 rho r. Right. Now everything that I need to include are already included. Then I'm going to apply this for 2 scenarios. Before applying to 2 scenarios, if we can see constants for these 2 scenarios, you better cut them off. See, 4 3 is common, G is common, 5 is common. Then only this part is needed. G dash is proportional to rho r. G dash is proportional to rho r. Right? So apply it. For first one, say GA proportional to rho is 2 rho here, r is r. For the second case, GB proportional to rho is rho there. Right? But radius is 2r. Divide these two. All unknown terms will cancel. right? And you are getting that GA over GB equals 1. GA over GB equals 1, right? Which means GA to GB ratio is, right? Ratio is 1 to 1. They are equal. GA to GB ratio is 1 to 1. GA to GB ratio is 1 to 1, right? So likewise, we can do necessary modifications, right? As our requirement is satisfied. Now my requirement is to include density. My requirement was to include density. Then I expanded mass as 0. M equals 0. V of a sphere is over 3 pi r cube. So likewise, we can do the modifications. Take it down. Write down. Right. Finish. Finish. Okay. Write down below with a red pen. Expand mass as 0. Write down below with a red pen. Expand mass. Expand mass as 0. Expand mass as 0. Expand mass as 0. Expand mass as 0. when a changing density or radius is given, 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 when a changing density or radius is given. Right, let's move on. As the next heading, write down work and energy. Write down sorry sorry next heading, write down work and energy in a gravitational field. 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 Right. So first thing is about work. About work. Write down work done. Heading, na? As a heading, write down work done. Work done. Look at the board. Take down the equation. Del W equals M delta V. Or it's also written as W equals M delta V. Delta के लिए भी not कौन है? W equals M delta V. Or delta W equals M delta V. But introduce terms. W work co-energy. W work energy. M moving mass. This is important. Not a static mass, moving mass. Alright. Delta V gravitational potential difference. Don't worry, we'll see what gravitational potential is. Gravitational potential difference. Gravitational potential difference. Gravitational potential difference. Gravitational potential difference. Right. So first of all, we'll see what a potential is. What potential is in gravitational field. Right. As the next heading, take down. Next heading. Potential of a point. Potential of a point. Write down. Next heading. Potential of a point in a gravitational field. Write down. Potential of a point in a gravitational field. Potential of a point in a gravitational field. Potential of a point in a gravitational field. Look at here. Potential of a point in gravitational field. Right. So let's say this mass is taken from, right? Let's assume a mass is taken from same mass. Mass is taken from infinity to point A at a gravitational field, right? Infinity to point A. Infinity to point A. Say B is infinity. Right? Now, if we apply this equation, considering this, the amount of work done, W equals M delta V. M delta V. Right? W is the work done. M is the moving mass. Moving mass, that is simple M. Moving mass is M. Delta V. Any delta is written as final minus initial, no? Right? So this is called potential at A. Potential at A is written as VA. Potential at A is written as VA minus potential at B. Minus potential at B. Right? Potential difference can learn. Gravitational potential difference. Final potential minus initial potential. VA minus VB. Right? But we know gravitational field intensity at infinity was 0. अब कल improve करा gravitational field intensity at infinity was 0. Right? If there's no gravitational field intensity, which means there's no gravitational field. Right? If there's no gravitational field intensity, which means there's no gravitational field. If there's no gravitational field, there's no gravitational potential. If there's no gravitational field, there's no gravitational potential. Then my argument is gravitational potential at infinity is 0. Right? You will see this as an equation again in the coming part. Gravitational potential at infinity, V infinity, is 0. Gravitational potential at infinity is 0. Right? Which means, see, W equals M VA minus 0. Then W equals MVA. We wanted potential. So potential at A is given by WOM. Potential at A is given by WOM. Right? So using this, we are going to define potential. Using this, we are going to define potential. So listen, potential of a point is defined as amount of work done. See, amount of work done to take a unit mass from infinity to point at a gravitational field or point on a gravitational field is called gravitational potential. That is called gravitational potential. Right? Take it down. Take it down. Take it down. Okay, done. Write down the definition in red. Write down the definition in red below. We are defining gravitational potential. Write down the definition in red. We are defining gravitational potential. Write down the definition in red. Write down amount of work done. Amount of work done. Write down amount of work done. Amount of work done on a unit mass. Amount of work done on a unit mass. Amount of work done on a unit mass kept at infinity. On a unit mass kept at infinity. Kept at infinity. Kept at infinity. To take it. To take it. To take it. To take it to a point in gravitational field. To take it to a point in gravitational field. To take it to a point. To take it to a point in gravitational field. To take it to a point in gravitational field is defined as gravitational potential. is defined as gravitational potential is defined as gravitational potential is defined as gravitational potential is defined as gravitational potential. Gravitational potential. Right. Find units and dimensions of gravitational potential. Find units and dimensions of gravitational potential. අපි V කියලා තමයි ලියන්නේ. V is W over m no. Work over mass. Then joules over kg, joules per kilogram. Joules per kilogram. Dimensions of work or dimensions of mass. Work and energy are same, ml squared t minus 2 over mass m. Right? Cancels. Then L squared t minus 2. L squared t minus 2. Right? Take it down. Next heading. Write down. Gravitational potential. Heading, na? Heading. Gravitational potential. Comma. Gravitational potential energy. Gravitational potential, comma. Gravitational potential energy. And kinetic energy. In a gravitational field. And kinetic energy in a gravitational field. And kinetic energy in a gravitational field. And kinetic energy in a gravitational field. Right. See? So this is a mass of this is an object of mass m. This is an object or a planet of mass m, right? And distance from here to here, distance from here to this point, let's say x. So we are interested about this point, say point P, right? මම මේකේ proof එකක් තියෙනවා, මම proof එක පෙන්නන්නම්, but we don't have the proof here in physics, but මම proof එක පෙන්නන්නම්. I will show you the proof, right? First we will mention all the equations, then I will show you the proofs. See? Right, this is how these three are defined. Gravitational potential at P. Gravitational potential at P. Right, that is something for the point. Gravitational potential at P is defined as minus gm of x. Right, gravitational potential is defined as minus gm of x. Right, then gravitational potential energy of simple m, right? So let's assume we have a mass simple m here, that is minus gmm over x, gravitational potential energy, right? Now, so from the beginning we have been writing gravitational potential energy as mgh, no, right? Wait a bit, I will show you. Right, in a gravitational field, that is minus gmm of x. Right, minus sign means, listen, minus sign means that, you know, in work power energy also I told you, minus sign means work is done by gravitational field. Minus sign means work is done by gravitational field. Right, work power energy we have a signage in work. So that is what we have here and here. Work is done by gravitational field. If we release this from infinity, it automatically comes back to gravitational field. Right? It comes back to gravitational field. Then it is done by the field. That's why it is minus. Right? Then kinetic energy of simple limb, right? So let's assume velocity of this simple limb as v, right? And this is the path of simple limb. Let's assume kinetic energy, velocity of simple limb as v, then kinetic energy is half mv squared as usual, right? Or else it can be written as gmm over 2x. It can be written as gmm over 2x, right? Okay, first take this down, then I will show you the proofs. Proofs won't be asked, right? But I don't need to like give these equations out of nowhere, then I will show how these things are derived, but it won't be asked. To get an idea, I will show you how it's coming, right? First mention these three, mention these three. Mention these three. Take it down. Finish. Mention below with a red pen. Mention below with a red pen. Mention below with a red pen. Minus sign refers to with a red pen. Na? Mention below with a red pen. Minus sign refers to. Mention below with a red pen. Minus sign refers to. Minus sign refers to. Mention below. Minus sign refers to. Minus sign refers to. Minus sign refers to. Work done by. Minus sign refers to work done by gravitational field. Minus sign refers to work done by gravitational field. Minus sign refers to work done by gravitational field. Minus sign refers to work done by gravitational field. Minus sign refers to work done by gravitational field. Right. See, I'm going to prove these ones. Look at the board. Look at the board. So we know gravitational potential energy that we knew before was mgh, no? Gravitational potential energy that we knew before was mgh. That was mgh, right? But we can't use mgh here in gravitational fields, right? Because of one main reason. What's the reason? Any guesses? Look at the equation and tell me. Gravitational potential energy is mgh. mgh. Why can't we use mgh here? I say we can't use mgh. What's the reason? Anyone? Any thoughts? There's nothing as correct or wrong. Just share your thoughts if you got any thoughts. Why can't we use MGH? Listen, listen. The reason is when you are moving here and there in a gravitational field, G changes, no? G changes, right? Then we can't use MGH because G changes. G changes. MGH is applicable at the Earth's surface or close to Earth's surface only. At the Earth's surface or close to Earth's surface. Now, in our mechanics things, that is totally fine because we are considering small heights when we are using MGH. Close to Earth's surface, right? About 300 meters, about 300 meters from Earth's surface, G starts changing again. Then actual value of G is 9.81. No? Second decimal changes beyond 300 meters, beyond 300 meters of an altitude. Then for these kind of things, we can't use G, we can't assume G as unchanged because it is rapidly changing. It is rapidly changing. So therefore, MGH cannot be used. Since G changes, we can write the same as mg dash h. No, how done mg dash h, right? We know how to write G dash at this point. We know how to write G dash at this point x distance away. अब ये प्रूव करा कोमन देख लियो G dash shows gm of x squared. No, first proof gm of x squared. The point is x distance away. Point is x distance away. Plug it here. Simple m G dash gm over x squared, and h means x now, vertical height, right? Then see what comes. It says gmm of x, gmm of x, right? This is gmm of x, and minus sign is due to work done by gravitational field. Magnitude is coming like this, right? Magnitude is coming like this, and minus sign is due to work done by gravitational field, right? Minus sign is due to work done by gravitational field, right? Then we'll put this minus manually because work is done by gravitational field. So this is the first proof. Now since G changes, now in this equation we don't have G, right? Instead we have gmm of x, right? So we can use it anywhere even if G changes. That's why MGH is converted to minus gmm of x in a gravitational field, right? Take it down. Take it down. Take it down. The reason to say this is some students think that for normal mechanics questions, gravitational potential energy is mgh, but for a gravitational field that is minus gmm of x, they are two different models, two different equations. No, that's the same equation in two different appearances, two different shapes, two different forms of the equation, right? Two different forms of the equation. Take it down. එකම equation එක තියෙන්නේ. හැබැයි MGH එක use කරන්න බෑ G change වෙන හින්දා. ඉතින් G change වෙන එකට මට G වලට substitution නම් මම මේ දීලා තියෙන්නේ. G වලට substitute කරා. කරලා මේක හොයාගත්තා. Right? Because I need to apply this when G changes, no? Take down. Okay. Right. Right. Now, using this, I'm going to prove gravitational potential at point P. Gravitational potential. Gravitational potential. We proved the equation before. We proved the equation before. It was W over M, no? Right? අපි potential එකට equation එක කලින් ගත්තානේ. When we are defining potential, right? V was, right? V කියලා ගත්තේ. Gravitational potential was V. V was W over M. Right? This was V. V was W over M. Now, if we consider this point, right? The only energy the point has is gravitational potential, no? Then plug it here. W is GMM over X. W is minus GMM over X, right? Divided by M. M to M cancels. It says potential equals minus GM over X. This is how potential becomes this. Take it down. This is how potential becomes this. Take it down. Take it down. Right. Then right. Next one is kinetic energy. For kinetic energy, to prove kinetic energy, if we consider the circular motion of simple M here, we can apply F equals ma towards center, no? Right? Using F equals ma towards center. Because actually what happens is this. Listen for a moment. Because of gravitational force, not energy. Because of gravitational force, right? This force acts. This force acts along this line. This force acts along this line. And this force is acting as a centripetal force. Since it's a centripetal force, the object undergoes a circular motion under this centripetal force. Because gravitational attraction is towards the center. Gravitational attraction is towards center. Right? That's a centripetal force, has a velocity, so it undergoes a circular motion. So that's why we can use F equals ma towards center. Then if we use F equals ma towards center, this F here is gravitational force. Expand it as GMM over X squared, right? Equals M. A, we know A can be written as centripetal acceleration. V squared dou R. Then this is V squared over X. M to M cancels. X to X cancels. It says V squared equals GM of X. Right? Now, our kinetic energy, our equation of kinetic energy is half mv squared, no? Half mv squared, right? Nothing changes in half mv squared. Even if g dash changes, no worries. See, half is same, mass is same, and velocity. Even if g dash changes, it is applicable. That is why we can apply this one. That is why we can apply half mv squared. But to take it to another form, now what I'm going to do is we can plug this v squared here. Half m v squared gm over x. Then it says that is gmm over 2x. Right? So that's how this came. Right? The thing, the idea I wanted to give you is these are not new equations. These are the different forms of the same equations you knew. Right? They are the different forms to cater this idea, to cater changing g. Right? to deal with changing G, right, we have converted our known equations, same equations, to a different form, right? Take it down. Proof, why did you put minus? Because work is done by field. Because work is done by field. Write it down. Kinetic energy එක prove කරන්න මෙහෙමයි. එතකොට මේ equations තුනම prove කරන්න පුළුවන්. තුනම prove කරන්න පුළුවන්. And you better know these links, right? අර වෙනම equations කියලා හිතන්න එපා. එහෙම නෙමෙයි. They are the same equations. Same equations. Right? But we have converted it into a different form. That's a thing. Right? Okay. Listen now. Listen. The next idea is this. Now you can see all these three equations here. When x goes to infinity, see, when x goes to infinity, this becomes 0, this becomes 0, this becomes 0, which means at infinity, there's no kinetic energy, there's no gravitational potential energy, or there's no gravitational potential. Nothing is there because there's no gravitational field at infinity. අපේ equation එක දන්නවනේ F equals G m1 m2 over r squared, right? Then when it goes to infinity, right, we have plotted the graph as well. When it goes to infinity, gravitational field intensity being 0. Gravitational field intensity 0 means gravitational field is no more, no gravitational field. Then from energies also we can get the same. When this goes to infinity, all energies become 0. All energies become 0. Write down below with a red pen. Write down below with a red pen. Write down below with a red pen. All gravitational potential. Write down. All gravitational potential. All gravitational potential. All gravitational potential, comma, gravitational potential energy, comma, gravitational potential energy, comma, gravitational potential energy, and kinetic energy. All gravitational potential energy, comma, kinetic energy, comma, kinetic energy becomes zero at infinity, becomes zero at infinity, becomes zero at infinity, becomes zero at infinity, right? Listen now. Listen. Listen. Now, today itself, we have covered around 75% of theories here, right? 75% of theory parts, 75% of theory parts in gravitational fields has been already covered, right? So next day, the other parts coming up are escape velocity, right? Then applications of energy. We didn't discuss any applications of energy and applications of gravitational force and gravitational field intensity, right? Those application types. Then escape velocity. Then neutral points, geostationary satellites, right? Those are the parts coming up, right? This is an interesting lesson, very interesting lesson, and a very practical lesson, and an interesting lesson, right? So we will continue the rest this point onwards next day. Any questions from the things we discussed today? Any questions from the things we discussed today? Raise your hand if everything is clear. Raise your hand if everything is clear, and raise your questions if there's anything to know. Clear. Right. Okay then. If no questions, we'll wind up. Right, we'll wrap up. If no questions, we'll wrap up. Then 18 weeks, 3 days remaining, 18 weeks and 3 days remaining. So work hard with your fullest effort, right? Work hard in silence and let your results make the noise, right? Then everyone will like talk about you, will talk the things about you with others, that this is how you did. That's better, right? That's better. You can work hard in silence and let your results speak and let your results make the noise. Okay then we'll wrap up. See you in the next class. And Saturday we are starting current electricity, right? Saturday we are starting current electricity, and S2 discussions are also coming now. I couldn't do it last week. For tomorrow also, I'm not sure, I'm not available, right? So other S2 discussions are also coming up, mainly thermal, elasticity, matter and radiation. Those parts will be coming up in S2S, right? So you can get the updates through channels and stay connected, and you can join those sessions. They will be all on YouTube now, right? Okay then if no questions, we'll wind up. Stay safe these days. Adverse heat conditions are going on, right? Stay safe and work hard. Okay then, see you in the next class. Good night and goodbye.